All right, ladies and gentlemen, today's class recording has started. All right. So just as a reminder, right, if you say anything stupid from this point forward, it will end up on the internet and for your grandma to see. So, because she'll probably watch it in between cat videos. So, I just assume grandmas watch cat videos. All right. So our next unit, and we kind of introduced this already off camera, but not there's a camera off recording, I guess, whatever. So our next unit deals with energy and different types of energy. Energy is, like I kind of mentioned before, a way for us to tie together different ideas and different concepts across units and make this class cohesive. If we watch the flow of energy in a situation, we can predict what's going to happen in that situation and explain what actually happens in that situation. So there won't be a unit moving forward from here when we won't discuss energy of some way, some form, somehow. Okay? So let's introduce a couple of the types of energy that we're going to discuss in this class. Some we'll discuss more than others, but we'll hit most of these as we go along. First, what is energy? That's a tough one. It's a hard, there's not like a real definitive definition. And you'll see when I put up here in a second how I define energy. It seems real vague, but it is the best way that I think we can use it to apply the energy concept to different areas. So I like to say that energy is the ability to do stuff. Which I realize is not scientific in any way, shape, or form, but it really is a way for us to apply this idea to different concepts. Oh, starting the one with the slides. Yeah, definitely, yes. The ability to do stuff? Really? Awesome. So there's some continuity there, you know? All right. If you want something a little bit more descriptive, we can also modify it to say the ability to move or change matter. But that's just a fancier way of saying do stuff. The ability to make things happen. The ability to make things different than they were before. That's the definition of energy. We measure energy in an SI unit called the joule, capital J. Named after James Joule, who did a lot of work with heat transfer and steam engines and things of that nature, so it's that. Joule is a derived unit, okay? So when we see joule, actually this is kind of a good transition. If you're watching the recording, you can't see it, but over here on the side, right, in my first period class, we were talking about the combination of units that makes up newtons, right? That whenever newtons shows up, it's really this combination of units, okay? When joules shows up, that is kilograms times meters squared over seconds squared, okay? So there's another meter thrown in there from newtons, but anytime joules shows up, it's this combination of base units. So probably a good thing to write that down, even though it doesn't show up on your notes, but that's a good thing to kind of keep in mind that when we use joules, it's really a combination of base units, and that will help us a little bit more on Monday when we start doing some calculations. All right, good there? Yep. So let's talk about some specific types of energy. First, mechanical energy. Mechanical energy is the type of energy that you have been introduced to in the past. As far as the definition goes, the energy associated with the motion and position of everyday objects. So if we break that down into regular person speak instead of this fancy sciencey stuff, right? Okay. Position describes where something is. Motion describes what it's doing. So the ability to do stuff based on where it is or what it's doing. Okay? Good? So mechanical energy is the ability to do stuff based on where an object is and what it's doing. Its position and motion. Right? Mechanical energy is actually a combination of different energies. We talk about kinetic energy, which I'm pretty sure you've been introduced to before. Potential energy, we're actually going to introduce another form of potential energy that you might not have been introduced to previously. Most of you are probably familiar with gravitational potential energy, which is height, okay? But there's also something that we'll call elastic potential energy. I don't know, did you guys get... Okay, so then I won't go any further with that, right? Elastic potential energy is just from stretching something, right? Or squeezing it down. Gotcha. Okay. So yeah, like I said, I know that you guys have done this before, so I don't want to like go too deep into it. Okay. All right. Good. Okay. And just to get it out of the way right now, okay, because so we'll get it out of the way right now, right? So it says P on the board. I know that I have to do that. Like so we'll get our laughs out of our system, and then we'll move on. So okay. So it is, and that's why I have to, you know, that's why I have to. So, all right, so thermal energy. The fact that it's thermal energy means it's associated with what? Heat, right? So heat, and we'll get into this in our next unit, is the energy associated with the movement of microscopic particles. And those microscopic particles can be atoms or molecules, depending on what we're talking about, and we'll distinguish those a little bit more when we get into chemistry later on, okay? So the energy associated with the small particles that make up an object, okay? Because it's movement, that means that thermal energy is actually a form of what? What kind of energy is associated with movement? Kinetic, right? Thermal energy is just kinetic energy on a really small scale. Okay? All right. The more movement that something has, the more thermal energy it has, the less movement, sorry, when I say the more movement it has, we're talking about the particles, the atoms and molecules that make up an object, the table that you're sitting at, the pencil you're holding in your hand, whatever. If there's more movement of those particles, there's more thermal energy. If there's less movement, there's less thermal energy.
So, when you rub your hands together,
Yep.
that's friction and it creates heat.
Yes.
Is that technically a part of thermal energy?
Yes. The motion of your hands is actually being transferred to the molecules that make up your hand, and that's why it feels warm. Because the particles in your hands, the molecules in your hands, are actually moving faster because of the energy that they're receiving from the movement of your big hands. Does that make sense? All right, next. Chemical energy. Chemical energy is important for your daily functioning. Chemical energy is energy stored in the chemical bonds of a compound. So when atoms come together and form bigger particles, molecules, right, and we'll get into that process a little bit more later in the spring, right, there's energy associated with that. Your body takes the chemical bonds that are in the food that you eat, the banana or the bagel or the macaroni and cheese that you had for breakfast, whatever, right? It takes that and it breaks it down. And as it breaks it down, it uses that energy then to make your heart beat or make your lungs expand in and out or like to run the race or whatever it is, okay? So chemical energy, the bonds of those molecules either get broken and then we use that energy for other things, okay? All right, good there? Okay. Electrical energy. Electrical energy is energy associated with electrical charges. I'm assuming you guys are familiar that there's two types of electrical charges. Yeah? Positive and negative, right? And they attract and repel depending on, what we're talking about. Okay? And as they attract and repel, right, we can use that to move or change other things. Okay? So as we attract or repel these positive charges and negative charges, we can use that attraction or repulsion to move other things. Like, if you have a toy car or a model car or RC, whatever, the wheels to move or whatever it might be. Okay? or like a ceiling fan in your house, those kind of things. All right, next, electromagnetic energy, which is a little different than electrical energy, right? Electromagnetic energy is actually energy that travels as waves. Somewhere along the way, have we heard of the electromagnetic spectrum? Right? So all the different types of waves that travel through our universe and through that we use here on Earth. Different waves have different amounts of energy that they carry, and then we can use them for different types of things. Is good.
Does this energy get into like
There are some similarities there, but there are some differences. All waves carry energy. Okay? So electromagnetic waves don't carry energy through something. They just carry the energy basically through themselves. That's why we can get light and heat from the sun, even though there's nothing between us and the sun, right? Surface waves are energy that is traveling through a material, right? So like an earthquake, the energy of the tectonic plates, that's kinetic energy because the plate moves, but then that energy is transferred through the earth so that it ends up, knocking down a tall building or whatever it might be, right? So there's similarities in that they both transfer energy from one place to another, but there's some differences in how they do it. Does that make sense?
yeah.
Okay, so yeah, some, but a little bit different. Okay. All right, and we have all these different types of electromagnetic waves, the whole electromagnetic spectrum, right? Some types of waves don't have enough energy to hurt us, like radio waves, right? This room is filled with radio waves from cell phones and radio signals and my computer talking to the projector and all the other things that happen, wirelessly, right? Those are all radio waves. They don't hurt us. But if you get waves that have more energy, like ultraviolet radiation, it could damage your skin, right? That's what we call sunburn, okay? Or on the really, really high end, when we get like into X-rays, right? Now we're talking about destroying cells in your body. Like when we use X-rays, if you've ever known anybody who has to go through radiation treatment for cancer, right? That's basically X-rays. We're hitting that part of the body with a high energy wave. Remember, energy is the ability to do stuff. If you have too much energy, it can kill things, right? That's what radiation treatments are. They're basically killing cancer cells, and that's what we're looking for there, okay? So the ability to do things. And then finally, nuclear energy. So like its name suggests, energy stored in the nucleus of an atom. And under the right conditions, we can turn this stored energy into released energy, and we can use it to power nuclear power plants, right? Electrical plants that are run on nuclear power, or destroy Japanese cities, those kind of things too. So, don't want to do that, but we could. Okay, so. All right, good? All right. So that being said, let's then move on to the other outline that I gave you today that deals with introduction to mechanical energy. Okay. As I've already said a couple of times, I've said it yesterday, I said it today, I am going to assume, and now especially because I know that you guys have talked about elastic potential energy, all the stuff in this outline you have heard before. So let's go through it, let's review it, make sure we understand some of those things, then we can apply it late next week, and then we can apply it to bigger and better things later on. Okay? All right, like we talked about before, energy. Our working definition of energy is going to be the ability to do stuff, or the ability to do damage, or the ability to change things, or the ability to make things different than they were before. Those are all the same thing, right? The ability to move or change other objects. And like we discussed, the SI unit there is the joule. The joule is a combination of base units. Here it is. Might be a good idea for you to write that down just so you remember that kind of stuff. right, good? Yes? All right, so let's talk about some specific types of energy, right? Before we introduce mechanical energy, the energy associated with the motion position of everyday objects. So because of where something is, the position, or what it's doing, the motion, it has the ability to change other stuff. Okay? That's how it all fits back to our definition of energy general being the ability to do stuff. As we discussed in the last section, right, when we're talking about mechanical energy, we actually add up a couple of different types of energy. We add up the kinetic energy, but then we also add up two types of potential energy: gravitational potential energy and elastic potential energy. And there it is, guys. Don't worry, by the end of the unit, it'll just... So we look at a combination of these three things that makes up mechanical energy. Even though all of them together make up the mechanical energy, individually they are different. So let's talk about those individual differences here just in a second. All right, good? Okay. So, kinetic energy. I think all the way back in like 4th grade you learned about kinetic energy, right? Kinetic energy is the energy of what? Motion, right? The energy of motion. Or if we apply it to our definition, right? The ability to do stuff because an object is moving, right? The ability to make things different because of its motion, right? Kinetic energy depends on two things. It depends on the mass of the object, and it depends on the speed of the object. All right, so let's get into a couple of details about this because they're important moving forward. And I'm assuming these are probably details that you haven't talked about before, okay? First, I described it as mass and speed. But when you look at the formula, what letter shows up there? V, which generally stands for what? Velocity. First, what's the difference between speed and velocity? Velocity has direction. Speed does not. That means velocity is a vector, but speed is a scalar. Alright? So, even if we put a negative velocity into this formula, mathematically, what are we doing to it? What are you doing to the velocity in this formula? You're squaring. Oh, sorry, by the way. When we have this formula here, 1/2 mv squared, only the v is squared. Okay? It's not the quantity mv squared, it's mv squared. Okay? So even if you put a negative velocity in this formula, what are you doing to that negative velocity? You're making it positive. When you square a negative number, it comes out to be positive, right? Can kinetic energy ever be negative? Nope. All right? Meaning, if kinetic energy can never be negative, what is that telling you about it? What kind of a quantity is it? Scalar. Energy doesn't depend on direction. A car driving 35 miles per hour towards the east on Hilliard Boulevard out there has just as much ability to do damage as a car driving 35 miles per hour west. Okay? Energy is a scalar quantity. It does not have direction. It is an amount. It has magnitude. We talk about how much damage it can do, but not which way, because that doesn't matter. All right? Good there? Okay. Also, mathematically, let's talk about these relationships, right? If you make mass bigger, what's going to happen to the kinetic energy value? It's going to increase as well, okay? If you make the speed bigger, what's going to happen to kinetic energy? It's going to increase, but by how much? Mathematically, what are we doing here? Well, yes, right? But mathematically, we call that what? We're squaring it, right? So, if we were, and I know you can't see this on the video, but whatever, okay? If we take the speed, let's say from 1 meter per second to 2 meters per second, right? How much does the kinetic energy increase? 4 times. The right-hand side of this equation, increasing the speed from 1 to 2, the speed goes up by 2, but what are we doing to speed on the right-hand side of this equation? Squaring it. You square 2, this side of the equation goes up by 4. Okay? What if we then made our object go 3 meters per second? How much does the energy go up? Yes. 6th period? I'll come see you during lunch. That's why I said 6th period, because that's when he has lunch. So he's a biology teacher. He doesn't remember like numbers. So that was on recording. So back to some numbers. 'Cause I don't know if Mr. Cuomo could have answered this question, right? So well, let's go from 1 to 3, right? If we make this 3, what do we have to do to 3 on the right-hand side of this equation? Square it. So now this side of the equation is bigger by how much? 9 times, right? That means the energy goes up by 9 times. Okay? Is that making sense to me? Is that making sense? Are we okay with that? Okay? So, what kind of relationship do kinetic energy and mass have? Direct relationship. What do we call this relationship? It's not inverse, because they're getting bigger, right? We introduced it at the beginning. Direct square, we give it a special name. We call it a quadratic relationship, right? Because if we start graphing this, right, what shape are we going to end up with? A parabola, all right? So if you graph speed versus kinetic energy, you end up with a parabolic graph, right? And that's what a quadratic relationship looks like on a graph. And that's why we call it the quadratic formula, right? It's for solving those kind of equations. So, just to finish up that point, right? What happens to the kinetic energy of an object if its mass... Ooh, that is a bad grammatical error. Sorry. Disregard. This. Okay, so, bye. My bad. Sorry. You wouldn't even notice, would you? I mean, it helps you pay attention if you notice. All right, so what happens to kinetic energy of an object if its mass is doubled? Kinetic energy is doubled, right? That means that it is what kind of relationship? Direct relationship. Okay? But, like we just discussed, what happens to the kinetic energy of an object if the speed is doubled? The kinetic energy goes up by how much? 4 times, right? Speed is squared in that formula. And we just gave that a name, right? What kind of relationship do we call that? A quadratic relationship. All right, so to illustrate this point, okay, some of you are going to start driving here in a couple months, yeah, getting there, close, maybe, some of you. Yes, and then some of you probably won't be till like next summer. So my birthday, I have a late summer birthday, so I didn't get my driver's license until like winter of my 2 years ago.
Yeah, I was like, one year. Because I was living in a very
All right, but So eventually, right, we're gonna start getting learner's permits and learning how to drive and all that fun stuff, right? Okay, so first day out in the car, you go to Crocker Park, okay, with mom or dad, okay? And it's your first time driving, so you're being really careful. And in the parking garage, it says the speed limit is like 10 miles per hour. What? No. So you're probably going to be going 7. And so you're going to be going 7, and you're going to be grabbing the wheel like it's like you're going to basically like turn the wheel. Anyway. So 10 miles per hour through no fault of your own. Right? You like clip the bumper of a car because you didn't quite take that turn wide enough. Because there was somebody who was like walking right in the middle of the aisle instead of walking over by the cars where they were supposed to. So you thought you were going to hit them, and you were just trying to be safe, and so it's that person's fault. Okay? Let's say that for argument's sake. Okay? It's that person's fault. Okay? All right. So 10 miles per hour. How much damage do you do to that other car? 10 miles an hour worth of damage, right? The bumper's got a dent in it, some paint is scratched. It's not real bad, okay? All right, next week, and then hopefully this doesn't happen to you, all right? I just want to make good points to this, okay? All right, so next week, you feel a little more confident, right? So now you're driving through, not in the parking garage, but through Crocker Park, all right? And now you're going 20 miles per hour. Okay? You're driving over by that section where like Aladdin's is, and then like Cheesecake Factory's on the other side, and the big fountain is there, even though the fountain's not running any. Like, and there's all those cars parked on the side of the road, and some kid like jumps out in between the cars, and you didn't see him, and so you swerve to miss the kid, but you run into one of the parked cars, going 20 miles per hour. See, again, not your fault, right? Not your fault. Well, you're a new driver, right? You just panic. You're like, ah!
So you played Mario Kart.
I mean, so.
You get those little glides.
Exactly. All right, so 10 miles per hour in the parking garage, paint's scraped, bumper's bumped, right? 20 miles per hour, right? How much worse of a crash is it? It's not doubled. It's not twice as bad of a crash. It's 4 times as bad of a crash, right? Because going from 10 to 20 is twice as fast, right? Yeah. So then if you're out on the road and you get into a crash going 30 miles per hour, it's 9 times as bad of a crash. If you're on the highway, and you're going 70 miles per hour, how much worse of a crash is it than the little fender bender you had in the parking garage? 49 times as bad. All right? So keep that in mind as far as speed goes, okay? All right, we'll finish up potential energy on Monday, maybe do some calculations and go from there. Have a good weekend, everybody. Oh, if you didn't look, there is some assignments on the calendar, but some of those questions might deal with potential energy. We didn't quite get to it. There's a section for you to read. That would be a good thing to do over